When NASA's Cassini spacecraft went to Saturn, it gave us close-up images of Saturn's moons, and it took pictures of the rings from a safe distance. And the reality is that if you tried to actually fly through the rings, it would be a very dangerous experience. It would probably have destroyed Cassini if it actually tried to make that journey. And yet, we want to learn more about those rings. My guest today is Dr. Mike Rubenstein. He is a professor of computer science and mechanical engineering at Northwestern University, and he is the recipient of a NASA NIAC 2026 award for a mission called the Actively Steerable Femtosat Constellation for In-situ exploration of Saturn's rings, atmosphere, and magnetosphere. This is an incredible proposal for flying a fleet of 10,000 tiny satellites that would aerobrake through the atmosphere of Saturn and then fly through the rings of Saturn. And the rings are so dense that most of the spacecraft would be lost with every fly through of the rings. And yet, if you send 10,000, then you will bring together some really interesting data and take some pictures of the rings from the inside. So if this idea fascinates you, enjoy this conversation with Dr. Mike Rubenstein. Mike, first, congratulations on winning a 2026 NASA NIAC grant. Is this your first?
This is my first, yes.
Yeah. And this idea is so cool. When I saw this one, this was like, I really hope Mike gets back to me. Come on. I want to be able to interview you on this one. So your idea is to observe Saturn's rings with a swarm of satellites. Tell me about the idea.
So the idea is to, instead of sending like a traditional, flagship satellite like Cassini or something like that, which is, a really good science platform, but it's also, because it's a single satellite, they're kind of trying to avoid risk of that satellite, right? So you don't want to send it anywhere near there's a chance of like a particle hitting it or anything like that. So we were looking at some advantages of swarms, and one advantage of swarms is that they're fault tolerant and they don't really rely on any individual working at all times. So we asked, like, maybe we could send them in a dangerous spot. What's the most dangerous spot that's scientifically interesting? And I think the rings of Saturn are pretty interesting. So the idea is that we accept the fact that if we go through the rings of Saturn or something at orbital speeds, you're going to crash into particles and lose them, the satellites. But if you have enough of them, it's okay losing half the satellites as they go through the rings. You still have many satellites after that.
Now, you have not begun the research yet. And I'm sure you are sort of still bringing yourself up to speed on the environment around Saturn and the kind of density of the particles. But have you got a sense of just like how dangerous that environment is around Saturn?
We looked mostly at just the event of going through the rings of Saturn. So looking at existing data about the particle distribution within different rings. And then given the size of our satellite, we know like what is the chance of a satellite being lost for different parts of the ring. So like the A ring, the A ring, which is kind of the outer part of the major rings, you lose about half the satellites as you go through the ring. The B ring,
wow.
The B ring, you lose 92% of the satellites. Cassini gap, you lose like 30% of satellites.
One pass through the B ring, you lose 90% of your satellites.
Yeah. So B ring is very dense compared to A ring, and even if you have our satellites are very thin and small, so they have a very small surface area, a frontal surface area going through the rings. But even going through the B ring is too dense for them.
Yeah. It's interesting. I think people don't realize just how thin the rings are, that they're in some cases 10 meters thick. Like the height of a house is the thickness of the rings, that you would just be above the rings. Now you're in them and now you're out the other side. But that density of I never thought that the density of particles was that high. I would have figured it would be more like the asteroid belt. I mean, not quite as loose as in that case, you've got hundreds, thousands, sometimes even millions of kilometers between objects that you would have to go out of your way to hit one. But you're saying that 90%, like what are the particles that you're going to be crashing into? Are they going to be like grains of sand?
Yeah,
or?
We're assuming that, at the speeds that we're traveling, like a grain of sand would destroy a satellite. So, my understanding is that, there's a distribution in density and there's lots of very small particles, probably down to like, beyond the size of the small in a grain of sand. And we just assume, based on the data we saw, like if you hit anything, you lose the satellite. maybe that's not the case, but we're just assuming that for safety. Yeah.
Yeah, but it's funny because like even this question, like you don't have the answers to the questions, which is why we need a spacecraft, and yet no spacecraft is willing to go anywhere near that sort of spinning blades of death. So it's like very self-referential. All right, so let's talk about your idea then. Like, what would these you're calling them femtosatellites? What would they look like?
So they're kind of like, what is the simplest satellite you could build? Can you make it as small as possible? It's basically like a PCB with a motor on it, a solar cell, and a battery and radio. What's a PCB? A printed circuit board, a little electronic board. Usually they're green, like inside your cell phone or whatever. It's just a bunch of electric components built together on a circuit.
Right. And so how small do you think you could get this down to?
We're estimating it's about 10 centimeters by 5 by 2. So it's, a little bit bigger than a business card.
Right. I mean, that sort of fits into like a fraction of the, like a CubeSat. Like the CubeSats are 10 by 10 by 10 centimeters. So that is, I forget, they're like a fifth of a CubeSat U or something. I forget. There's a standard.
I think 10 by 10 by 10 is a 1U. I'm not sure though.
Is 1U. Yeah. Yeah. And so you're a slice of a U.
Yeah. So, I mean, the idea is you can have, a cubic meter of these things. They weigh, like all together, they weigh maybe 300 kilograms. Takes a cubic meter, and you have 10,000 of these satellites in a cubic meter.
Wow.
So by making it very small and simple, you could build lots of them that don't weigh too much, right?
Right. So one of the challenges, of course, is when you're out at the orbit of Saturn, the amount of energy you can get from solar power is like 1/100th, 1/25th. I forget the number, but it's a fraction of what you get at Earth. Is there enough power to get, like, is the solar panel the primary thing you're having to deal with?
I mean, that's part of what we're looking at in the study, is trying to kind of go from ballpark estimates to like understanding, like, a little bit more with more certainty. Can you power something with a solar cell? Can it survive the temperature? Can it survive the radiation environment? Those are all things that we think may be possible. It's not like completely out of the realm of possibility, and we just have to kind of dive into the details and understand that a little bit more.
Right. This is what this is what the research is going to be. And so then one of the other things that you mentioned in your initial proposal was that there would be some kind of propulsion system. Have you thought about what that might look like?
So there's no propulsion system. They use aerobraking for maneuvering in orbit. So the initial orbit starts kind of the lowest part of the orbit just touches the outer atmosphere of Saturn, and the highest part of the orbit goes a little bit past the A-ring. And then when you go through the atmosphere of Saturn, you actually lower the point where you cross the ring of Saturn. So we can control the drag on these satellites through the aerobraking to control like where they touch the ring of Saturn when they pass through them. So satellites have one motor, and they have two kind of passive directions they could pass through the rings through the atmosphere. One is like a face-on, so a very high drag configuration, and one is edge-on, so very low drag configuration. So you can control how much drag the satellite has during that, aerobraking, and that allows you to control where it goes through the rings of Saturn.
Right. Okay, so take me through the whole story. You are, you've handed off your meter cube of femtosatellites, and it's been packed atop a rocket, and the rocket blasts off on the way to Saturn. How does the rest of the mission unfold?
So I think nothing really happens on the satellites themselves until you release them in this initial orbit. And then they immediately start taking passes through the rings of Saturn. Every time they go through the atmosphere, they slow down to control where they go, and they make another pass through it. And, you lose like half the satellites every pass, but just based on the initial estimates, you can have, I think, 200 satellites actually make it through the entire A-ring, going like 7 or 8 times through the A-ring themselves. 100 satellites will make it through the A-ring and then make it through the Cassini division, and then a few will make it through the B-ring and stop. So you'll have like all these satellites getting lost as they go, but you'll make 10,000 passes successfully through the rings of Saturn, even though you're losing lots of them.
Right. And I mean, I'm sort of imagining this aerobraking maneuver where you've got this, would they be a clump of satellites and then they're like a little bit stretched apart and then they're all making their way through the atmosphere? I mean,
ideally they'd be as far apart from each other as possible. So I don't, colliding within the aerobraking is probably something that would break the satellites. So hopefully when you release them in their initial release, you spread them out a little bit. So that way they don't collide with each other. And after that, there's very little chance they could collide with each other through the rest of the mission.
Right. And then one of the great challenges is transmission. So how would you get the information home once you're sort of sending these poor little satellites through their depth dives?
Again, that's another question that we're trying to answer for the proposal or for the phase 1 study. The thought is that maybe the initial mothership that dropped them off in orbit will still be in orbit and can, if it's a large ship, has a very high gain antenna, it can receive radio information from the satellites and then broadcast that back to Earth once the satellites have transmitted to them.
And so what do you think is like the biggest source of risk at this point? What sort of freaks you out?
So, I mean, there's lots of like development questions, solar power, radio power, and, looking at the details of those, making sure it's still feasible afterwards. One thing that's fun about these satellites, which is kind of novel that enables this mission, is the way they actuate themselves. There's not actually onboard propulsion. They use a single motor to control their orientation in space as they're flying around. And looking at that controller is something I think is very interesting because it's not intuitive how to get a single motor to point the satellite in 3 degrees of freedom. And when it's trying to, face the rings or face the sun to recharge, or reach these 2 drag states for the aerobraking.
And like typically this is done with reaction wheels on spacecraft, and they need minimum, I think, 2, ideally 3, to be able to control it in the 3 axes of orientation. How do you do it with 1?
Yeah, so the reason that we want to have 1 instead of 3 is you could have 3 times as many satellites, maybe, because the wheels probably take up a lot of the space and a lot of battery consumption on the robot. So making them as simple as possible is why we're kind of pushing it down to 1 motor. And the way we actually control the 3 degrees of freedom is that we have a motor, and at the end of that motor is a mass with a spring attached to it. So like there's a spring between the motor and the mass. And if you spin the motor at slow speeds, that spring doesn't do anything. But if you spin up faster, that spring will stretch out, and then you kind of get your moment of inertia changes as you're actuating the motor. So you can spin up quickly and spin down slowly, and then once you reach the motor in the original position, you'll now be in a different attitude. So it's kind of a non-holonomic controller for the satellite. So it's a little bit...
Oh, that's brilliant.
So it's hard to control, but you can kind of go through these sequences of motion where you control both the position and the speed of the motor, and you can end up pointing it in any orientation you want it.
And this is a thing that you've tested out and
that's part of the study, but we're pretty confident that we can get that to work.
Yeah. I mean, that alone, I mean, there was, I don't know if you've been following the news, but there was this mission to try and recover or help boost the orbit of the Swift satellite. And there was a booster satellite that was launched just like last week, and 2 of its reaction wheels failed. And so it's down to 1.
Right.
And they think they can recover it with the propulsion system, use its ion drive to get it back on target. But if you just had only 1 motor, I guess 2 is 1 and 1 is none. So then of course there's that whole question of redundancy. But if you can just even operate on 1 just purely by the spring mount that is around your reaction wheel motor, that offers up some interesting ideas. Like, now I'm just spitballing here, but like if you go back to say the Kepler mission, that mission failed because of the loss of its reaction wheels. But if you had this sort of hybrid version where you have the motor, reaction wheels, but it's inside a housing that can kind of act like another axis if you need it.
Yeah, I think if you build and plan ahead for this type of control, you'd have to kind of have the motor in a unique position, and it may not be the same type of motor you'd use for like these high-speed flywheels. but it would be possible to use this type of mechanism on a bigger spacecraft. One hard thing is that I think most of these spacecraft care not only about pointing at a particular direction, but tracking something in a smooth motion. And this control that we have it can't track, it can only point. So think of like if you're driving a car and you want to go from pointing in one way to another, maybe you have to do lots of weird back and forth until you point in the right direction. This does something similar to that. So if it's pointing one direction, it needs to go to a different direction, it might do a bunch of strange wiggles and then eventually restart.
Right. So you're not going to be tracking, say, some target perfectly as you're moving. You kind of end up where you need to be through a lot of, a very messy set of movements. That makes sense to me. But still, it's kind of interesting how there's this idea that I'm really excited by where there are various metamaterials, various kinds of existing stuff that naturally wants to solve a problem. That instead of you trying to come up with some kind of engineering solution for it, which is a potential point of failure, you use the right kind of material that can, or the right kind of configuration that provides you that solution just as part of the process. And so it's like one less point of maintenance and failure and so on. If the underlying just structure of what your thing is made of,
right?
These various bimodal metals or things like that, right?
I think there's a trade-off between like the traditional systems, which are, I guess, easier for engineers to understand and easily control, and then these more exotic systems that are maybe more efficient in mass or something like that, but are not easily controllable or not very intuitive to understand how to do that. Yeah.
So did you start with what could we use swarms to study in the solar system, or did you start with how could we study the rings of Saturn?
We start from the question of swarms. So that's my research background. I build swarm robots. So trying to understand how to build lots of simple things and control them to do behaviors that we care about as a group. And we've been looking at one motor vehicles for a few years now. And the question is like, can we have a one motor vehicle in space? And then, by going to one motor, you can make them very small. And then make lots of them for the same type of payload and mass. And the question is, what's a mission that can take advantage of that capability? And that's kind of where we landed with this going to the rings of Saturn idea.
And so were there like second ideas? What were some other places in the solar system that you thought might be interesting to send this kind of a swarm to?
So not only is it fault tolerant, but it's also distributing sensors across a wide spatial area. So you can we have some algorithms for getting them to spread out equally in an orbit. So you start them all in like one clump, and then you come back a few weeks later and they're equally spaced along the entire orbit. And that way you can have lots of sensors along lots of areas. So maybe if you care about looking at like very quickly changing magnetic fields on a planet, like maybe Uranus is important to understand the magnetic fields, then maybe this is a mission that would be helpful for that instead. Because if it's changing very quickly, it's hard to measure that from a single point that's moving around.
I mean, I'm thinking about something that, like, for example, say the plumes on Enceladus, where you could send them in a stream through the plumes. Yeah, you're going to have some are going to get hit by ice or whatever, but you're going to then be able to measure the dynamic quality of the plumes. Are they changing in strength and so on as materials blasting out?
I mean, having them go through would be helpful, but like, how do you get them to move in that way is a hard problem to do, and that's why we take advantage of this aerobraking around Saturn, which should probably be harder to do around a moon.
Yeah, to try and aim to do your aerobrake
right.
and get through the plumes
right.
at Enceladus, which is however many millions of kilometers away from Saturn. The other idea, a lot of people are thinking about these tiny spacecraft, even smaller versions, chipsats, for interstellar probes. This was the idea of the original Project Starshot. And there are how do you make these things small enough and accelerate them to relativistic speeds you can cross between here and another star system in a small amount of time. But the other issue is communication, that you won't be able to send the flagship mission. And so, in fact, these tiny spacecraft can work together to mimic a larger radio dish that could be sending a transmission home.
Yeah, I mean, I feel like that's an order of magnitude harder problem than the one I'm looking at. So I'm looking at using mostly easily available components. Like there's nothing novel about any individual components that would be going on the spacecraft. It's kind of just the control behind them and maybe the motors as part of the spacecraft. What you're talking about, I assume, is building the entire thing from scratch out of nothing you could buy currently.
Probably,
right.
but I think that people have jumped straight to, well, let's build an interstellar probe, and I think what you're addressing is let's develop swarms to explore the solar system, and then you could do things like, well, instead of them being carried on a giant carrier spacecraft, let's attach a solar sail to them and accelerate them with lasers. And maybe now you're sending 10,000 tiny satellites to 10,000 different asteroids. That is, you're not getting that swarm, but even swarms exploring individual asteroids is a very interesting process as well. But just this idea of us getting really comfortable exploring the solar system with small satellites, as opposed to trying to make them, large flagships, that disposable nature.
I mean, I think that's cool idea. I think, having a swarm like this lets you distribute them spatially. So now you can set a satellite to every asteroid that you know about. And, it makes it low cost and fault tolerant. If you're sending it to every asteroid, you miss one of them, it's probably not that big a deal.
Yeah. Yeah. The idea that I liked about this to solve the communication gap is that you send them on trajectories that will then bring them back to the Earth. Mm-hmm. So you pick an asteroid, you send the small sat towards the satellite. It does a flyby, reaches the very height of its perihelion and then, its aphelion, and then comes back down to Earth and does a flyby and then transmits its data when it's close to the Earth, and then, can be disposed of or goes off to another target. So, but now I'm just rabbit holing. Well, Mike, what are you obsessed with right now?
I mean, a lot of stuff I've been doing has been looking at robot minimalism. So I'm really interested in, like, how do you get robots to be as simple as possible and still do the things that we care about in robotic systems. So instead of having a four motor flying robot, can you with one motor? Can you have like a satellite that has one motor? Can you have any other type of robot that's very simple but yet capable of doing the things you care about? And that makes it easier to build lots of them.
I mean, it really, for me, is like, when do they wash my dishes?
You have a dishwasher, which is a robot that everyone has.
Yeah, I know, but it's not picking up the dishes from the cabinet, and it's not pulling them out of the sink, and it's not putting them away when it's done. It's good,
but it's
a
really hard
enough.
Problem.
Yeah, I know. Yeah, I think that is the line for most people, which is that if you can have a robot, that even a flying robot with knives for hands, I don't care, have it come through and do my dishes and clean up after me, and I think we'd be willing to accept any kind of risk. I sort of imagine Terminators stepping on the skulls of humans in the future. It'd be fine.
As long as they're cleaning your dishes.
Yeah, for 10 years, we had our dishes done.
Right.
Yeah, and then the robots took over. Fine. It was worth it, though. Yeah. Well, Mike, congratulations on the NIAC grant. Good luck with the missions that you're working on, and I hope to see the pictures from Saturn's rings inside the rings. That'll be crazy.
Yeah, thank you.
I hope you enjoyed this conversation with Dr. Mike Rubenstein. As always, I did another longer version of this exact interview where we talked about another project that Rubenstein and his team are working on, which is to make an invisible drone. So it's called the Phantom Twist, and it is a drone that the entire object spins so quickly that, kind of like how a propeller on an airplane makes it so you can't see the propeller, now you can't see the whole drone. Now, it's still very loud, but it is much harder to see. And actually, the goal is not to make an invisible drone, but to make a safer drone for people to be able to be nearby. So if you want more information on drones and just kind of like drone society in general, I think you'll really enjoy this longer version of the interview. As always, it's over on Patreon, but it's completely free, open access. You won't see any ads. I'll put a link down in the show notes so you can go and check it out. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bodu, Carradine, Chuck Hawkins, Commander Baylock, Dark Finga, David Giltonen, David Matz, Enthrall Reading and Math for Toddlers, Evan.pro, James Clark, Jeremy Mattern, Jim Burke, Marcel Smits, Michael Purcell, NASA Ocean Guy, Nordspace, OneStepForAnimals.org, Please follow my nephew at vbrick6994, Ring Kaidu, Richard Williams, Sean Sargent, Stephen Funlemonley, Team 49, Telescopes Canada, Vlad Shiplin, Wolfgang Klotz, Zelda. Oh my god, we have proof of aliens who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. Well, this is great. I'm really enjoying my run through the NASA NIAC Awards so far. This is the third one that I recorded. I've got at least another 5 in the queue so far. I think there's 18 that were released this season, and as always, I'm going to try and get every single one of them to talk to me. If not, well, that'll be too bad, but I'll try. And I hope you're enjoying them as well, as much as I do. And of course, we're going to have all of the interviews in a collection on Patreon or on a playlist on YouTube. And so if you want to go back through not just the ones that we've done this year, but the ones we've done in previous years, they are all just bonkers ideas, totally out of left field, out of the box thinking, technological readiness level 0. But these are the kinds of ideas that may be able to eventually carry humanity to the stars. All right, we'll see you next time.